In this video, we're going to talk about hybridization. What is it, why is it, and what do you do with it? So hybridization occurs in order to accommodate bonding that will result in a stable configuration for an atom's orbitals. And the easiest way to look at that is if you look at carbon to start. Carbon has 6 total electrons and it has 4 in its outer shell. If it didn't undergo hybridization or a blending of its orbitals in order to basically even out their energies so that they fill up symmetrically, what you would end up with is the first energy level S subshell, which I have buried in there. You have the second energy level S subshell, spherical in shape, would have 2 electrons in it. And then out of the 3 p orbitals, you would only have 2 of them with an electron in it. And that would result in the ability to only bond to 2 things with those single electrons. So you could form CH2, which doesn't satisfy its octet rule and is not very energetically favorable. So what's going to happen is it's going to hybridize those orbitals into 4 sp3 orbitals, we call it, because it's a combination of an s and 3 p orbitals that blend together to become equal energy. And then once they're equal in energy, according to Hund's rule, you'll fill up each with 1 before you put 2 in any. That results in each 4 energetically even orbitals, each containing 1 electron. And that would allow it to bond with 4 hydrogen atoms and complete its octet shell, and complete the octet rule, and make it stable. So what you have to do with this is all you have to do is be able to count. You just add up the number of atoms bonded to the central atom, or whatever atom you're looking at, and the number of unshared pairs on it. And that will tell you the number, that will be equal to the number of orbitals that have to hybridize. So if you have 2 orbitals that have to hybridize, that's going to result in an sp hybridization. 3 orbitals, sp2. 4 orbitals would be sp3. And then if you have some elements in the 3rd period or below that have d subshells, sometimes they can have more than 4 bonds. So they, like pf5 has 5 atoms bonded to it. That would have 5 orbitals that hybridize, so that would be sp3d hybridized, and then 6 orbitals would be sp3d. So talking about single bonds, what we showed over there, now we're going to talk about a molecule that has a double bond in it. You have formaldehyde here, which is CH2O. The carbon wants to form a direct link with all of the atoms present. There are only 3 atoms there that's bonding to. And it hybridizes those 3 orbitals so that they can spatially spread out in an optimal fashion. They get into basically a trigonal planar molecule shape. And then what happens is you have one of the p orbitals remains unhybridized. The reason that that happens is if it's going to form a double bond between the carbon and the oxygen, it can't basically squeeze in 2 hybridized bonds directly in between them. They would end up being too much repulsion. So what happens is one of the p orbitals remains unhybridized, and it's an original 2-lobed dumbbell shape. This green is 1 p orbital, and it would have 1 electron in it available to bond. The other 3 end up forming bonds, 2 of them with the hydrogen and 1 with the oxygen. And then what happens is those p orbitals basically reach around the bond that's already formed, that first bond, to form a pi bond, which is the second bond formed between any 2 atoms. And it's not directly in line, and it doesn't require a hybridized orbital. So what you end up with for a molecular structure is right here, where you have those pi electrons shared between the p orbitals that are unhybridized. Now, one thing I also want to point out, the oxygen is an sp2 hybridized atom as well. You have 3 orbitals that are hybridizing, the 2 unshared pairs, and the one that's involved in the sigma bond, which forms between the carbon and the oxygen. The reason these 2 need to hybridize is all about spatial arrangement. They want to spread out to the point where they're equally repulsive to each other. I guess that doesn't sound too good, but essentially it leads to also having a trigonal planar shape between those. And then you would have the unhybridized p orbitals that result, p orbital, that results in a pi bond between sitting on top. So, just to recap, sigma bond is the first bond formed between any 2 atoms, and it's a result of the bonding between 2 hybridized orbitals, with the exception of hydrogen. Hydrogen can't hybridize, it only has 1 orbital in its outer shell. And then a pi bond is a second or more, so second double bond will do this, a triple bond will involve. It's the bonding between 2 atoms formed from unhybridized electrons in unhybridized p orbitals. So looking at these three structures right here, I already mentioned pf5 here. Phosphorus is in the 3rd energy level and has d subshell, so it's capable of forming an sp3d hybridization to accommodate the 5 bonds it needs to form that are going to be equally spread out from each other, resulting in this trigonal bipyramidal shape. The ammonia has 3 atoms bonded to it and an unshared pair. And all of these are essentially going to become equally repulsive to each other. Kind of, there's a little exception there. But they're all hybridized, and you would end up with an sp3 hybridization there. If we look at this last molecule right here, you can see that the carbon has only 2 atoms bonded to it. And essentially, between the carbon and the other carbon, it has 1 sigma, and it would have 2 pi bonds, resulting in a triple bond there. Since it only forms 2 bonds, no unshared pairs, we're going to call that an sp hybridization. Only 2 orbitals required to hybridize, so it's sp. I think that one was a little better.